Hi, welcome to lecture 12 of ECE 113. In this lecture, we will be talking about the Smith chart. So what is the Smith chart? It's this one. Alright. So just a note, it's a very useful tool for RF engineers. Okay? Such elegance. Very elegant. Yeah. How do you use this? That's the question. Alright. So, kind of looks like an alchemy circle or something. Anyway, I won't talk about that. So, this is the Smith chart, and it's a useful tool. Okay, it's a useful tool for RF engineers. For the purpose of this course, well, it can be used for impedance matching. Okay, impedance matching, amplifier design. Okay. So that will be the use of the Smith chart here. So it's a graphical aid, very useful for solving RF circuit theory problems. It's an integral part. It can be used for computer-aided design software and microwave test equipment, and it's a must-have tool for any high-frequency engineer. Okay, so that's your Smith chart. It's composed of circles and arcs. It's basically a polar coordinate system. Okay, so let me just write that. It uses the polar coordinate system, and it's graphing the reflection coefficient gamma. So basically, it's a graph of gamma. Any point within your circle here corresponds to some value of gamma, or the reflection coefficient. Right? So that is your Smith chart. So this would mean that this axis is the imaginary axis and this axis is the real axis. Right? Let me just change the color of the pencil. Okay, let's use blue. Right, there we go. So this is your real axis. Okay. So that's what I told you earlier. Your Smith chart is the graph of the reflection coefficient. So the reflection coefficient is related to the load impedance by this equation, where Z0 is your characteristic impedance. Okay. So just some notes. When your source and load impedance are not complex conjugates of each other, your maximum power transfer is not achieved. So that's the concept of impedance matching. We use impedance matching to transfer the power from the source to the load. Ensure that there are no reflections. Okay. So that is characterized by the reflection coefficient. There are reflections. If your source is matched to the load, then this will be 0. And it's generally a complex number. Okay? So it has some real part, let's say U, and some imaginary part V. Okay? So now let's define what we call the normalized impedance. First, before we go into the details of the Smith chart, the normalized impedance is basically your impedance divided by your characteristic impedance. And just a note on the notation, lowercase letters would represent normalized quantity. So it's normalized quantity, and a uppercase letter would be your actual value of your quantity. Okay? So if we use the normalized impedance, so in terms of the reflection coefficient, we get this equation. So it comes from the equation of the reflection coefficient, ZL, let me just delete that. There you go. So ZL minus Z0 over ZL plus Z0. If we factor out Z0 from both sides, we get a ZL divided by Z0 minus 1 over ZL divided by Z0 plus 1. And this is your normalized load impedance, which corresponds to this lowercase z sub l right here. And generally, of course, since this is complex, okay, then we can represent it as this in terms of Euler's identity, the magnitude times e raised to j times the phase. So from this equation, we can solve for ZL, And ZL is a function of your reflection coefficient, magnitude, and phase. So the derivation of the Smith chart comes from that equation right here. If we let your ZL have of course, a resistance and a reactance. So resistance and reactance. And gamma, of course, has its own real component and imaginary component. By substituting that to this equation, we get this equation right here. Okay, so that's what you have here. And we separate them in their real and imaginary forms. How do you do that? By multiplying the complex conjugate of the denominator. So let me just clear that so it would be easier to understand. So if we multiply this by the complex conjugate, let's just use black. If we multiply this by the complex conjugate, which is 1 minus u plus jv, okay, so 1 minus u plus jv right here, the denominator will become purely real, and what separates the real part and the imaginary part would be defined by the numerator, and you'll get this equation. So this is the real part and this is the imaginary part. So which you can separate them into those components. The real part is equal to this, and the imaginary part is equal to this. And these two equations are the basis of your Smith chart. Smith chart. There you go. So if we rearrange the equations, so you know u and v would represent dots in the basically the dots in the polar coordinates. Since we're plotting gamma in the Smith chart, this u and v would define any function in your Smith chart. Okay, so if we rearrange the terms as a function of u and v, turns out that if you have a constant resistance, you get a circle in the Smith chart, and if you have a constant reactance, you also get a circle in the Smith chart. Okay, so the center of the Smith chart is when u is equal to 0 and v is equal to 0, and that would make it the matched condition, or if your ZL is equal to Z0. Okay, so if you look at this equation first, the equation for constant resistance, okay, and if you look at that, your center is defined by this, and since you don't have any term inside the square of v, then your center will only be defined by a shift in u, which is the real part. So the centers of all your constant r circles lie along the real axis of your Smith chart. The constant x circles would be on the line, okay, since your u is displaced by 1, the center is displaced by 1 unit, and your y-axis, your v-axis rather, your imaginary axis, your center is displaced by 1 over x depending on the reactance. The centers of the x circles would lie on the u is equal to 1 vertical line. Okay, so to draw the Smith chart, you need to get the constant resistance circles and the constant reactance circles and mix them together to create the chart. By using that, you will be able to identify the resistance, the impedance of a given reflection coefficient. Okay, so basically you use the UV plane, okay, which corresponds to the polar plane of your gamma. So plug in values of constant r and constant x, we get circles. Okay, so first let's look at the case of the boundaries rather of the Smith chart. Your resistance is between 0 to infinity, a short circuit and an open circuit. Okay, if it's a short circuit, the equation becomes this, which is the equation of the unit circle. And if we draw that, it's not here, there you go. It's the biggest circle there is. if your resistance is infinity, your constant resistance circle becomes this. The radius of the circle is 0. Therefore, sorry, let's use another letter. So the radius of the circle is 0. That would represent a dot. And that dot is located at u is equal to 1 and v is equal to 0. So that is centered at 1, 0. A dot centered at 1, 0. That would be this dot right here. So anything in between, so a resistance in between would mean that your radius is decreasing and your center is constantly displaced in this direction. So this is the constant resistance circle. Any point on this, let's use another color for your pen. So let's use blue. Any point on all of this circle would mean that in the normalized impedance, your R is constant while your reactance is varying. Okay, that is the constant reactance circle present. So now let's look at the reactance. And again, it can also be written from 0 to infinity. Its value is also from 0 to infinity. A short circuit and an open circuit. Okay. So if it's a short circuit, then the radius of the circle is infinity and its center is located at infinity. So it's a circle, quote unquote. That means it's just a line. Okay. So it's very far away. So let's say the center is right here. If we measure the distance from here to here, it's infinity. This is infinity, this is infinity. Could be equal. Okay? So it's indeterminate. Therefore, it could just be a line. We can model it as a line. Okay? So that is your constant reactance circle when you have a short circuit. When it's open, okay, when you have an open circuit, then your constant reactance circle would just be a point, the same point as what you got earlier for a constant resistance circle. So it's this point. Okay. So that means anything in between, okay, is a constant reactance circle. Or could have any reactance rather, anything in between that. So from here, this is the constant reactance circle. And it turns out that any combination of R to X in magnitude, okay. So any value of R and X can be plotted in your Smith chart, okay. So any physically realizable impedance is within the unit circle. Anything beyond that would mean that gamma is greater than 1, which is, well, it's not physically realizable. You get a reflection coefficient greater than 1. That's weird. Okay. So the constant reactance circle, so this is the ones in brown would be the extreme case. This one is when you have a 0 reactance, and this one, the dot here, is when you have an infinite reactance. Anything in between would be defined by these circles right here. Anything on the top half of the unit circle is inductive, since your reflection coefficient, the reflection coefficient here, the imaginary part, V, greater than 0, corresponds to an inductor. And anything below, in the southern hemisphere of the circle, semicircle rather, the lower semicircle correspond to V is equal to V less than 0. That means your device is capacitive. Okay. So with that, since we're going to take advantage of the fact that gamma is equal to ZL minus 1 over ZL plus 1, that means gamma uniquely determines the impedance. Okay? So taking advantage of that fact, that means any point on the Smith chart right here corresponds to a unique impedance. The impedance here won't be equal to the impedance here, won't be equal to this impedance here, and it won't be equal to this impedance here, and so on and so forth. Okay, so how do you read that? If you look at this point, it's on a constant resistance circle. Okay, excuse me. It's on a constant resistance circle corresponding to 1. Excuse blue. Okay, corresponding to 1. And it's on a constant reactance circle corresponding to plus J1. Then the impedance here is equal to the normalized impedance is 1 plus J1. And so it's a load impedance. To get the actual load impedance, you multiply this by the characteristic impedance Z0. There you go. This is the load impedance that is on this point given in the Smith chart. Okay? So that's how you read the Smith chart. Right? So each load impedance, oops. Okay, there you go. Each load impedance ZL corresponds to some reflection coefficient gamma and vice versa. Okay. So there you go. Another important use of the Smith chart is the measurement of what we call the standing wave ratio. So the standing wave ratio is directly related to the reflection coefficient gamma. Okay? And since ZL is equal to this, if we let theta is equal to 0, then we get the SWR. Okay. And what that means is if we take the magnitude gamma, we're just concerned with the distance of your reflection coefficient from the origin. And getting that distance from the origin would mean you get the SWR. Since you're getting the magnitude of gamma, that's the same as getting the distance of gamma from the origin, and you get some constant SWR circle. As long as you're equidistant from the origin, your SWR is constant. That would mean your circle, constant SWR circle, is basically centered at the origin, whose value is dependent on the radius of that circle, or the distance of any point on the circle to the origin. So that's the one use of your Smith chart. So SWR is a measure of antenna match. Common measure for antenna matching. Okay. So we can also use the Smith chart to plot admittance. Okay, so in the previous discussion, we use the impedance. So we use a normalized impedance mapped to some gamma. But we can also use this and plot the admittance, which is the reciprocal. Okay? So just note that this reciprocal can be rewritten as something like this. So if you look at this and this, turns out that Y, the normalized admittance, is just a phase shift pi from the normalized impedance. There's just a phase shift of pi in between them. That means if you just rotate the Smith chart by 180 degrees, you rotate it by 180 degrees, you get an admittance chart. Okay, so that's what I was telling you earlier on this slide. So to have an admittance chart, we get something like this. And the admittance can be read at any point. If you have this point right here, this is a constant susceptance circle right here. And this is a constant conductance circle. So this corresponds to conductance. Okay, and this one corresponds to susceptance. Susceptance, if you don't know, is equal to the reciprocal of the reactance. Alright. So, however, if you mix and match both two of them, it could be very confusing. So it could be, so it's actually, my head hurts just by looking at this. If you don't want to use that chart, then what you do is, let me just delete this. So if you don't want to use this, let's go back to, sorry, maybe better if you use, there you go, no, not this one. There you go. So if you don't want to use a chart like that, it's painful to use, there's a lot of details, okay? You can still use the same Smith chart that you see here, okay? So just note that if you want to get the admittance of this point, so the admittance of this point, you need to rotate it 180 degrees, okay? So form a circle from the origin, rotate that 180 degrees, so it's somewhere here, okay? So that is 180 degree rotation, the other point on the circle. This point corresponds to the admittance of this point, okay? So the admittance of this point, so that would be 0.5 minus J 0.5. So that is the admittance of this point right here. So we can do that instead of using something like this right here. Alright, so both methods are valid. If you don't want to use something as confusing as this one, well, you can just rotate, right, using a compass, of course, and there you go. Okay, so that's what this slide is telling us. Right. So why use an admittance chart? Because if we're using impedance, then it's useful when we have series connections. So you want to get the impedance of this. Since they are in series, this one has an impedance, this one has an impedance. We can just add them in the Smith chart. If you're looking at impedance, since the total impedance of this is equal to the sum of the impedances. The admittance is useful when you have shunt connections. So if the components are connected something like this, there you go. You have admittance 1 and admittance 2. The total admittance is just the sum of the admittances of these two. And you can just directly add them in the Smith chart, the admittance Smith chart. Okay? So for example, consider a circuit when you have a series impedances. The total impedance is just the addition of the two separate impedance. Okay? And if we break them down to real and imaginary components, then only the real and imaginary components will add, and you have something like this. Okay, so that's RL plus RS and XL plus XS. Right, so these are normalized, just note, normalized impedances. Alright, so the path is something like this. You start at the load, ZL, and if you increase your load, you add your resistance by RS. That means you have a constant admittance. Then the path looks like this. Okay, so you move from one constant resistance circle to another. Okay, and the value of the constant resistance is RL plus RS. So you move from RL resistance circle to RL plus RS resistance circle, and then from here you add the admittance XS. So the admittance, that would mean you're going to move on the constant resistance circle defined by RL plus RS, and you move this way. So the path that you took is from here towards here and from here towards here, and that is the how you use the Smith chart to determine the reflection coefficient. Okay, so you can, from here you can get the reflection coefficient of the sum of the loads here and here, or the sum of the source impedance to the load impedance. So from here, you can already obtain the reflection coefficient. You already have some information on the reflection coefficient of your series lumped circuit. Okay, or you can do the other path. If you add a reactance first and then add a resistance, you get to the same path, and that's what we're talking about in this slide. So you add your impedance, your reactance first, and you move in this direction. Then you add your resistance, you move in this direction. So take note that you are moving on a constant reactance circle. Okay, so the other way around is something like this. So you add the resistance first, you're moving along a constant reactance circle, and from there you add a reactance, and you're moving along a constant resistance circle. Okay, so both methods arrive at the same point C. Now, if you have a shunt lumped element circuit, then the total impedance, or admittance rather, of these two is just the sum of both. There you go. And the movement is, well, it's similar. You add the real components and the imaginary components, you'll get the same movement as you got before. You start at some point A, which corresponds to the admittance of the load right here. Okay, and then you can take two paths. Let's say we take the one where you add a susceptance first. You add a susceptance, then you're going to move in this direction. Okay, so you add a susceptance, you're going to move in this direction. So you add in this direction, and then from here you move towards the final point C by moving on a constant susceptance circle, and then you move to another constant conductance circle rather, and that's how you use the admittance part of the Smith chart. Okay, so there you go. It's the same method as your series lumped element when using the impedance chart. Okay, so how do we use it then? So a special case of your two applications is when your series or shunt elements are purely reactive. If you have a series L, series C, shunt L, and shunt C. And where do you find that? You can find that when we're trying to match your source resistance to your load resistance. We try to match that. First you get a series L and then a shunt capacitance. We can use them, or we can use the Smith chart to determine the values of these components without doing the tedious numerical analysis. Okay, so how to do that? First, you normalize everything by Z0 or Y0. Okay, so always get the normalized impedance or normalized reactance first. Okay, and you move in 4 different directions from the point. So let's say you start at point A. If you have a series L, that would mean you have a constant, since this is a series, then it's a constant resistance. Okay, a constant resistance circle is defined by this large circle right here, the one in blue. Okay, so you move in that constant resistance circle. So if you're series L, then you become more inductive. You move further towards the upper region rather of your circuit, of your Smith chart rather. Okay, there you go. If you have a series capacitance, again, since it's in series, it's a constant resistance, then you move in the constant resistance circle still, but the movement is going downwards since you're going into the capacitive region of your Smith chart. You're going downwards. If it's a shunt inductance, then that means you have a constant conductance, which is defined by this smaller circle on the left side of the Smith chart. If it's a shunt inductance, you become more inductive, then of course the movement goes towards the positive or the upper region of the Smith chart. Otherwise, if it's a shunt C, then you're going in the opposite direction, going towards the more capacitive region of the Smith chart. Okay, so there's no need to memorize on the movement. You just need to build an intuition. Right. So, some observations. That's what I said earlier. If it's an inductor, you move upward. If it's a capacitor, you move downward. Right? So, for example, find the input admittance of a combination of load. So, this is the load. And a shunt inductor of 8 nanohenry at the frequency of 1 gigahertz, assuming that the characteristic impedance is 50 ohms. Okay. So, first get the normalizing factors. To get the characteristic conductance or characteristic admittance, you divide, or you get the reciprocal rather of Z0. So you get this one. From there, you get the susceptance of the shunt inductor. To get the susceptance, it's equal to negative J over omega naught L. Basically, it's 1 over J omega L. Okay, and you get this. Divide that by the normalized admittance, you get this. Okay, and you locate the normalized load impedance ZL. So you normalize ZL first, divided by Z0, you get this value. Locate that. So it's somewhere here. It's 1 plus J, somewhere here. And you're going to add an inductor that is connected in parallel or shunted. Then since it's shunted, you're going to move in a constant conductance circle right here. And then the movement is upwards because it's an inductance. So you move from negative J.5 minus J. So it's negative J1.5. You end up in this point right here. So this is the final point, which corresponds the admittance of the total admittance of this circuit. And to get your Z in, you just need to get the reciprocal of that. Okay, so there you go. Okay, so get the reciprocal of that, and we may also read the impedance from the Smith chart. So the impedance in the Smith chart is this. Multiply that by Z0. So this should be Z0. You get 10 plus J 30 ohms. Okay, so that's how you use the Smith chart. So say we have this problem again. So more elements. Series, parallel, find Z in. Okay. With that, we can start by plotting first, locating the point ZL on the Smith chart, and then finding a path. So that's what it says here. So first locate your point A. Okay, let's say it's here. And a series positive, let's say all of these are all positive. Okay, so XS1 is positive, BP1 positive, XS2 positive, BP2 also positive. Then if you have a series inductance, which is positive X, then you're moving upwards towards point B. Point B, you have a shunt element, which is, let's say it's positive. Then you're going in this direction, and you end at C. You have a series, you end at B. So, and then finally, because of this, you go downward. And finally, you can solve for Z in. Right? So it's a useful tool. Instead of going through the tedious calculation, how do you solve for the input impedance of this monstrosity right here? Well, first you need to get the series of this. You add the impedances, then get the reciprocal of that. The reciprocal of that, you get the admittance, then you add that to the admittance right here, and so on and so forth. It's actually tedious. But if you use the Smith chart, you just need to locate the final point. from the final point, you can get the input impedance based on the constant resistance circle and a constant inductance circle, or constant reactance circle rather. So a direct application of the Smith chart is to use it in matching. So we can design an L network matching even a pi and T network using the Smith chart. So what is the goal? So the goal is to move the load impedance right here to the center of the Smith chart. We want to move that to the center. Okay? And what type of matching you will use, it depends on where you will locate your load impedance. If it's inside G is equal to 1, is it inside R is equal to 1, or is it outside both of them? So those are the three distinct regions we'll use. So what type of matching network you use, it depends on where is your load impedance. Okay, so case 1, you're inside R is equal to 1, then you have two possible movements to go to the center. Could be go here, go upwards until you hit R is equal to 1 circle. Okay, you move in a constant conductance circle until you hit R is equal to 1. Then you move downwards from there. The other way around is, again, you move in a constant conductance. Okay, you move in a constant conductance, you hit this point, and then you move in a constant resistance circle until you hit the center. So the first movement is a constant conductance movement. That would mean you're connecting a shunt element to your load impedance. Okay, that's the first step. After you move in a shunt element, you connect a series element to move in a constant resistance circle. So this is the type of circuit that does that behavior. Okay. So this is what I told you earlier. So the next case, so that's just some animation. Okay, there you go. The next case is when you're inside G is equal to 1. And when you're inside G is equal to 1, let's say you start here. Okay. So you start here, then you need to move in a constant resistance circle first until you hit the G is equal to 1 circle. Okay. So you can go either way. And then you get these two. Hi. So from there, you move in a constant conductance circle until you hit the center of the Smith chart. Okay, just a note that you assume here Z0 is equal to the source resistance. Okay? So just a note here that Z0 is equal to the source resistance. That's why we want to hit the center. Anyway, so the first step of your second case is you move in a constant resistance circle, and that is achieved when you have a series impedance. And after that, once you hit G is equal to 1 circle, you're going to use a parallel. So you're moving in a constant conductance circle. You need to connect a shunt element. Sorry. There you go. You need to connect a shunt element for you to be able to match ZL to your RS. Okay? So, okay, that's what I told you here. And this is some visualization of that. So you connect a series first and then a shunt. And finally, the third case, if your ZL is both outside both R is equal to 1 and G is equal to 1, you can have any path. Actually, the goal is you just need to make sure that ZL will hit G is equal to 1 or R is equal to 1. So that's the first goal. First step, hit either R is equal to 1 or G is equal to 1 circle. Once you've hit them, you're already on the path towards the center of the Smith chart. And from here, actually, you have 4 possible paths. Let me just outline it for you. Okay, let me clean that first. The first possible path is through here. The second possible path is through here. Third possible path is through here. And the fourth possible path is through here. There you go. So there are 4 ways to match a load that is outside the both of the circles. Okay. So there you go. So you can either start with anything, but rule of thumb, you always choose the shortest path. Right? Rule of thumb, always choose the shortest path. Choose shortest path. Okay, just the rule of thumb. All right. So in this case, the shortest path would either be this or this. Okay. So these are possible solutions for the matching. Okay. In this case, you're able to use different elements, or same elements rather, for the match. Okay. So yeah, this is what homework I gave you. That's the end of this lecture. It should be lecture 12. Sorry. If you have any questions, do not hesitate to leave a comment in the comment section below. Thank you for listening. See you next meeting.